Good morning to one and all. Once again, I welcome you all to the thermodynamic course. Myself, Arun Kumar K, Assistant Professor, Aeronautical Department from MLR Institute of Technology, Hyderabad. So, in the previous lecture, we discussed about the basics of heat engine, heat pump, or refrigerator. We discussed, right? And we derived the performance parameters also. So, the first unit actually we didn't derive any. We didn't discuss about any performance parameter, but whereas after applying this sign law of thermodynamics, we'll come to know how to calculate the performance parameter like efficiency, or we can say coefficient of performance. That is what in the previous lecture we discussed. So in today's lecture, we are going to discuss about some application kind of problem with respect to the heat engine and refrigerator. Right. So straight away we'll move to the problem. So first we'll discuss about the heat engine problem. So this is the question given. So the heat is transferred to a heat engine from a heat source at a rate of, right? So at a rate of 80 megawatt they have given. If the rate of waste heat rejection to the sink is 50 megawatt, determine the net power output and the thermal efficiency for this heat engine. So this is a simple problem we are having, right? So we are provided with heat supplied, right, from the source to the heat engine, and from the heat engine to the sink, heat rejection also they have given, right? Obviously, the 50 megawatt is nothing but this is what actually we are term it as heat rejection to the sink. This must be lesser than the QH or QS, whatever it may be, right, from the source. Right, so they have given us 80 megawatt. So 80 megawatt is supplied to the heat engine. In that, 50 megawatt is rejected as a we can say this as waste energy. Right, so these are all comes under losses. So the losses actually they have mentioned, I can able to easily calculate the efficiency also. Is that right? Yes. So it's a very simple numerical problem we are having. See, we know that how this heat engine is working. This is a hot source and we are having the sink from QH, right? This is what the QH is given us 80 megawatt they have given. From this 80 megawatt, how much energy get wasted? 50 megawatt is get wasted. So obviously the work done is nothing but we know that QH minus QC or QL, whatever it may be, right? So we are having as 80 minus 50, 30 megawatt only. We have converted that into useful mechanical work done. So remaining are considered as a waste energy. Because of the surrounding, it get transferred to the sink, right? So the work done is nothing but net work output is nothing but actually we call it as how much? 30 megawatt actually we have calculated, right? See, we know that the net power output is the difference between the heat input and the heat rejected for the cyclic device, right? See, the W net output is nothing but we call it as QH minus QL. So how much actually we are having? 80 minus 50, we got as 30 megawatt, right? Similarly, how to calculate the thermal efficiency? We know that the thermal efficiency is nothing but always the network output, right? Output by input we are having the efficiency. So the network output by input. So what's the output actually we are having? We got the 30 megawatt as the work output, and what about the input actually we are having? 80 megawatt as the work output. So we'll get 30 by 80, we will have 0.375, or we can say 37.5 percentage is the efficiency of the given heat engine, right? If the heat engine is rejecting 50 megawatt with the supply of 80 megawatt, I'll get 37.5 percentage as the efficiency, right? So this is what the thermal efficiency actually we got, right? Okay, na? So 37.5 percentage is nothing but actually that's a achievable one, right? So not to compare that whether we can able to achieve this or not, we are having the ideal conditions also that later classes will discuss. In the upcoming lecture, we'll discuss about the Carnot cycle, right? So that is what the comparison we required actually with respect to the ideal and actual cases. So these are all the assumptions actually I said, right? we are not having any the data with us. So 80 megawatt I have supplied and 50 megawatt I have rejected as heat, right? So with that, whether it is possible or not, with the given temperature, with the given source temperature and sink temperature, is it possible or not? Like that, we supposed to calculate, right? Yes, this is about the heat engine problem. Next, actually, we'll discuss about the refrigerator problem, right? So the problem is given us: the food compartment of a refrigerator is maintained at 4 degrees Celsius, right? By removing heat from it at a rate of 360 kilojoule per minute, right? If the required power input to the refrigerator is 2 kilowatt, determine the coefficient of performance of the refrigerator as well as the rate of heat rejection to the room that houses the refrigerator, right? See, I need to maintain the food compartment. There is a freezer space actually they have provided. That food compartment in a refrigerator, 4 degrees Celsius I supposed to maintain, right? By removing some heat from it, right? So heat is removed from the 4 degrees Celsius. So for this refrigerator, the 4 degrees Celsius is nothing but a sink actually we are having, right? How it is removing actually? By applying, by the expenditure of 2 kilowatt. See here actually they have given kilojoule per minute. We can able to convert that in terms of kilowatt also. So kilowatt is nothing but watt is nothing but actually 1 watt is nothing but 1 joule per second, right? So with respect to that kg per minute actually 60 minutes we are having, right? Sorry, per minute we are having 60 seconds, right? So with that actually I can able to get the how much kilowatt it is converted. So that's a just a unit conversion we are having. We supposed to calculate the COP and the rate of heat rejection to the room, right? That houses the refrigerator. Okay, na? Heat rejection to the room in the sense we supposed to calculate the QH, right? Yes. How to solve the problem? See, the refrigerator is given. The refrigerator is nothing but it is working under the cyclic process, right? And it is having the food compartment we need to maintain at 4 degrees Celsius, and that heat is sent to the warm surrounding, right? See, this is what how much work input actually we have given. Input is nothing but 2 kilowatt they have given. And what about this QL actually? QL is nothing but from the food compartment we are observing the heat energy through this refrigerator device, right? With that actually we can able to reject how much 360 kilojoule per minute we can able to release. That we can able to convert that in terms of joule per second also. Okay, now see, we supposed to know that always transfer to the which one source, TH. This is what we are having, TL, low temperature. Always this is TH is nothing but source. So QH is nothing but the heat transfer with respect to the source. We supposed to calculate that to QH also, right? See, COP is nothing but the desired effect by work input. Already we know that. Which is the desired effect? QL, right? QL is nothing but, see, listen here, 360 divided by 60, right? So we'll get 6. We'll get 6 kilowatt. We'll get 360 divided by 60. This is in terms of actually we are getting in terms of 6 kilowatt, right? 6 kilowatt. So like that actually I can able to get. So 6 divided by how much heat work input actually we have provided? 2, right? So 2 kilowatt we have provided. So kilowatt get cancelled. We are having 6 by 2. We'll get 3. So the COP of this particular refrigerator is nothing but we got us 3, right? And see, the COP of the refrigerator is 3 and 3 kilojoule of heat is removed per kg of work supplied, right? Okay, na? Yes. Then the rate of heat rejection can be obtained by applying the first law of thermodynamics also. That what is it actually? That is what the energy conversion we are having. So QH equal to, we know the mathematical relation, QL plus W net in, right? So QL already we know that 6 kilowatt already we calculated, and plus 2 kilowatt. So the overall the heat supplied, right? Heat rejection from that which one? Refrigerator is nothing but and it is supplied to the source, right? How much we got? 8 kilowatt we got, right? So in this way we need to solve the numerical problem on heat engine as well as refrigerator or heat pump, right? So this is applicable to the heat pump also. Instead of this QL, actually we supposed to consider as QH. Then it comes under kind of heat pump problem, right? Yes. Thank you, one and all. So we'll see in the next lecture. Thank you.